Tremendously exciting news. Gravitational waves have finally been detected. Here's a brief explanation. Back in 1915, Albert Einstein gave the world his new theory of gravity, the general theory of relativity, which is based on the beautiful idea that gravity is nothing but warps and curves in the fabric of space-time. Now, barely a year later, Einstein pushed this idea one vital step further. You see, he realized that if space is flexible enough to warp, then it should also be able to ripple, to vibrate, to undulate. And that would mean that if something were to jostle the fabric of space-time, it should send out ripples in the fabric of space, and it's those ripples that we now call gravitational waves. Now, of course, the source of gravitational waves would not be my hand jostling space. Instead, it would be some highly energetic astrophysical process like rapidly orbiting neutron stars or black holes that would send out a steady rumble of gravitational waves. Or at least, this is what the theory says should happen. Now, how do you test this idea? Well, the math shows that as a gravitational wave rolls by, it will squeeze and stretch anything in its path. You see it happening here for the Earth, but of course, this is highly exaggerated so you can see the effect. When you do the calculation, you find that the amount of squeezing and stretching would be tiny, a mere fraction of an atomic diameter, and that makes it pretty difficult to detect. But that is what the LIGO team has now achieved. And they did it with two detectors, one in Louisiana, the other in Washington State. And in these detectors, what they do is they fire laser beams along two 4-kilometer-long evacuated tunnels. And when the light recombines, it creates an iconic pattern. It's known as an interference pattern. But the only thing that you need to grasp is that were a gravitational wave to roll by, it would squeeze and stretch the arms of the detector, and that would have a measurable impact on that interference pattern, causing it to shift. And it's just that kind of shift in the interference pattern that the LIGO team has now observed, the first direct detection of gravitational waves. And this is big. This will go down in the history of science as a pivotal moment. And not just because it's another spectacular confirmation of Einstein's ideas, which it is, but rather because for millennia, we have explored the universe using waves of light. This discovery marks the opening of a new era in which we will explore the universe using waves of gravity.
Okay, well, what is it that scientists are so excited about? And astronomers and physicists are really agog at what's going on in the field of physics today, especially in regards to the discovery of gravitational waves. Now, what are gravitational waves? Gravitational waves are ripples in the fabric of space-time that are caused by the motion of masses. Now, the denser a mass is and the faster it moves, the bigger ripple it's going to make in space-time. We've got one example here, which is a binary system of a star. It used to be a double star. Most stars are not single like the Sun. Most are in multiple star systems, double, triple, quadruple stars, sometimes up to 6 stars all orbiting each other. Now, if one of those stars is a high mass star, say between 4 and 8 solar masses, it can go supernova, and then what will happen is it will create a pulsar, a neutron star, which is a stellar remnant, a very dense stellar remnant. Now, neutron stars are, as the name implies, are neutrons packed shoulder to shoulder. So they're very, very dense. Although they're only about 20 kilometers across in diameter, they contain the mass of about 1.4 up to 3 solar masses of mass. That means they have a magnetic field on the surface which is roughly 1 trillion times that we have on the surface of the Earth. And a teaspoonful of material from a neutron star will weigh 1 billion tons if you brought it to Earth. If the core of the star, when it went supernova and collapsed, when the core collapsed, if it was greater than 3 solar masses, then it would create a black hole. Here we've got a binary system of a neutron star and an ordinary star, and they are creating ripples in space-time. Every mass that moves in space-time creates a ripple, but some are obviously very small. For example, the Earth itself, as it moves through space-time, creates ripples in space-time, but it's not possible to detect them. They're too small. The ripples that the Earth creates are roughly equal to 1 kilowatt of energy per hour, so it's very, very minuscule. Now, pulsars create a lot more energy, as you might expect, because of their density and their rapid motion, especially if they are in a close orbit with a star or another neutron star, as we've got here. We've got two neutron stars, two pulsars orbiting each other. As they lose energy, they lose angular momentum. By releasing that energy as gravitational waves, they spiral in towards each other and coalesce. That was the discovery that LIGO made on September the 14th last year. Around about 1,000 scientists have been working on this, trying to detect gravitational waves. LIGO was first constructed in 1994 and it's been in operation for many years, but it was upgraded last year, and now it has 10 times the sensitivity that it had prior. Now, to detect the gravitational wave when it hits the Earth, you need to detect incredibly small movements in the arms of the LIGO detector. The arms are 4 kilometers long, and you need to be able to detect a motion, a shrinkage and a stretching in those arms, which is about 1,000th of the width of a proton. Now, this is a simulation of the two black holes merging that LIGO detected last September. One of the black holes was calculated to be 36 solar masses and the other one 29 solar masses, and the resulting black hole was estimated to be 62 solar masses. So around 3 solar masses is estimated to have been lost as gravitational waves during the merger. That is an enormous amount of energy. During that split second of the merger, more energy was put out than all the rest of the universe, the observable universe, put together. So it's a tremendous amount of energy that was put out during what they call the chirp. And this is what they've been looking for in the LIGO detector, is this chirp. Which involves the merger of the two black holes. So gravitational waves is the future for astronomy, one of the futures, as well as using light waves and radio waves. Now we're going to be able to detect objects in the universe using gravitational waves. It's a whole new field of astronomy, and it's very exciting for astronomers.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you made this long enough, if you didn't make it a little pipsqueak thing like this, but you made it sort of kilometer scale, you could probably get these extremely precise measurements.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
The precision that was required was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.